Have you ever wondered about the biggest explosion humans have ever seen? A supernova, the extremely bright, super-powerful explosion of a star, holds this record. Let's dive into the cosmic world to unravel the mystery of these celestial fireworks. Picture a star at least 5 times the mass of our Sun, burning massive amounts of nuclear fuel at its core. This process generates an incredible amount of energy, heating the star's center to unimaginable temperatures. This heat creates a pressure that pushes outward, balancing the inward squeeze of gravity. It's a delicate equilibrium, the lifeblood of a star. So what happens when a massive star exhausts its nuclear fuel, cools off, and the pressure drops? Gravity, the relentless force, wins this cosmic tug-of-war, and the star suddenly collapses. Imagine an object 1 million times the mass of Earth imploding in just 15 seconds. The rapid collapse generates enormous shock waves that explode the star's outer parts, marking the birth of a supernova. What remains after this spectacle is a very dense core and an expanding cloud of hot gas known as a nebula. If the star was more than about 10 times the size of our Sun, it might leave behind the densest object in the universe, a black hole. But there's another way a star can go supernova. Picture a binary star system, where 2 stars orbit one another, and at least one of them is an Earth-sized white dwarf, a remnant of a star the mass of our Sun. If one white dwarf collides with another or pulls too much matter from its companion, it can explode into a supernova. These events are so bright that they can outshine their entire galaxies for days or even months and can be seen across the universe. The study of supernovas has offered scientists a wealth of knowledge about the universe. For instance, the second type of supernova serves as a cosmic ruler, helping to measure distances in space. But that's not all. Stars, including their explosive ends, are the universe's factories. They are the cosmic factories producing the chemical elements essential for everything in the universe. In their fiery hearts, they forge simple elements like hydrogen into more complex ones such as carbon and nitrogen, fundamental components of life itself. It is only these massive stars that have the capacity to synthesize precious heavy elements like gold, silver, and uranium. When these titanic stars meet their explosive demise as supernovas, they fling these vital elements far and wide across the cosmos, seeding the material needed for planets, stars, and even life on Earth. NASA scientists use a number of different types of telescopes to search for and then study supernovas. One example is the NuSTAR, Nuclear Spectroscopic Telescope Array mission, which uses X-ray vision to investigate the universe. NuSTAR is helping scientists observe supernovas and young nebulas to learn more about what happens leading up to, during, and after these spectacular blasts.
Now that you've mastered the supernova basics, it's time to buckle up and prepare for an out-of-this-world tour. We're zooming through the cosmos to Cassiopeia A, the superstar of supernova remnants nestled in the constellation Cassiopeia. Not only is it the brightest extrasolar radio source in the sky for frequencies above 1 gigahertz, but it's also a stunning spectacle of cosmic chaos and beauty. Thanks to the Webb telescope, we'll dive deep into the heart of this celestial explosion, so hold on tight and enjoy the tour of Cassiopeia A.
Cassiopeia A, or Cass A, is a supernova remnant located 11,000 light-years away in the constellation Cassiopeia. Cass A measures about 13 light-years, or 76 trillion miles across, and is estimated to have exploded about 340 years ago as seen from Earth. In this image of Cassiopeia A, we witness a complex and dynamic system, a star that has explosively shattered, creating a shock wave colliding with the gas shed by the star before its explosion. The white smoky light is the aftermath of this event, representing radiation produced as the forward shock wave encounters and interacts with the surrounding medium. While Cass A has been observed by many telescopes, Webb's high sensitivity reveals never-before-seen details. Within this image, we encounter minuscule fragments, tiny ejected bits of stellar debris comprised of sulfur, oxygen, argon, and neon, shown here in bright orange and light pink hues. The dark voids in the scene are caused by some of the minute fragments acting like shrapnel. piercing through the circumstellar gas and leaving a trail of cosmic bullet holes in their wake. Also present are what astronomers call light echoes. With these light echoes, we're seeing where the original light of the supernova has been absorbed and reprocessed as infrared light by surrounding interstellar material. It takes many years for the original light to travel this roundabout path. By observing this journey, astronomers are able to learn more about the object that emitted the light in the first place, the composition of the region, and the distances between celestial objects. Finally, we visit a particular light echo from an area filled with intricate dust patterns. Nicknamed Baby Cassiopeia A because of its proximity and connection to the large supernova, Baby Cassiopeia A appears to be nearby but is actually located 170 light-years behind the supernova remnant. The unprecedented detail captured in this new image of Cassiopeia A has allowed scientists to discern intricate small-scale structures within the remnants of a supernova. This newfound infrared clarity, only possible with Webb's instruments, enhances our understanding of the processes surrounding supernovae. By studying objects like Cassiopeia A, astronomers can unravel the complexities of stellar explosions, trace the distribution of elements, and gain valuable insights into how new stars and planetary systems form.